All right, welcome back to the second part of today's lecture. I left you with this particular problem, and I wanted to just make you aware of what's on Blackboard is this two great notes. It has problems and solutions. So there's one note which looks like that, and we've got all the problem, like a lot of problems and solutions. So I highly recommend you use this as practice. Especially for for your exams and things. There's a lot of them. What's nice, it's all solved, all nice and neat. So that's the one, and the second one is this one. So yeah, highly recommend this. So use this for your practice. So you can't say that you don't have enough practice for balancing, and obviously the exercise in your textbook. But I like this notes. I wish I could have developed enough of them for all your stuff, but unfortunately, yeah, it's not the case. Okay, so for that particular problem, that is problem one. So if you've solved it, that is your MR cos 0.034, MR sine 0.74 kilogram meter. That was your resultant. Your mass was 7.48 kilograms, and your angle was basically 92.6. So you've done this fantastic. What I also did here is sketch the graphical method for you. So have a look at this one. But like I said, this is still at S3 level, and but those two notes will obviously yeah, you have all the things to work through essentially. Okay, so let's move on to where we need to be. So I'm going to back to the slides. Okay, so I just want to, like I said, take the other slide of mine. Where was it now? That's the one. Okay. Okay, so now we graduate, if I could say that, to what's the word I'm looking for here? Dynamic balancing. Okay, right. So where does dynamic balancing come to the fore? So we talked about static balancing being the vertical up and down, where your dynamic balancing has two parts, up and down and the left and right. And but essentially where it's mostly used, or this is where this analysis comes forward, is when there's several masses rotating in different planes. So in this case here, this is the case of different planes. So they have an illustration here where one mass is there and the other mass is there. And obviously this illustrates this over here. Because, previously we said one mass in the same plane. Like as an example, in the same plane what I mentioned, they're rotating about the same axis, such as a fan, a gear, and an impeller there of a pump. So obviously the masses would be the impellers rotating around that axis. But now that's on the same plane, but this is what we mean by different plane. So we'll get to that now. Okay, let's state there, we have several masses rotating different planes. So the centrifugal forces, in addition to being out of balance, also for couples or moments. A system of rotating masses is in dynamic balance when there is no resultant centrifugal force and as well as resultant couple. Very important. So there are two conditions which has to for the system to be balanced. It must be, the couple has to be balanced and the resultant centrifugal force. I'll talk about that now. So yeah, okay, cool. Yeah, so again, it's talking to this, where the forces must equal 0 and the sum of the couples must equal to 0. So the sum of the forces is the MR product, which you've done now, it's in the same plane, and also the sum of the MRL product now. And you understand why we have the MRL product. So I'd rather use this. Okay, so the conditions for masses in the different planes again. The forces in the reference plane must balance. The resultant force must be 0. That's the MR. And the couples of the reference plane must also be balanced, which the resultant couple must be 0. So this is what it actually looks like. I want to show you this. So what I mean in different plane is that imagine this shaft being here with bearings at O and Q, and we have one mass rotating there. Or let me rather use one in the middle. One mass rotating there, another mass rotating there, another mass rotating there, and another mass rotating there. Does it make sense? So you guys see there's a distance between mass 1, mass 2, mass 3. Yeah, mass 1, mass 2, mass 3 along the shaft. Can you guys see that? Do you understand what I mean in different planes? It's basically along the length of the shaft, there's different masses rotating. You guys got that? Are you guys following? So this is what I mean by a different plane. So before, all the masses were rotating, let's say on one, they're all rotating there, but now they're rotating at different parts along the shaft, and hence, due to that, it basically, there's two types of balances. One will be the static one, as we know, and also the dynamic one, which is the couple, which obviously includes the length now, well, at a particular thing. So what this is, well, let me just revert back. So just to give you an image, this is from the side view. We have different masses, mass 1, mass 2, mass 3, and mass 4 rotating. And this is, if you look at it from the front, you see this image over here. And what we typically do here, we have to add two masses for static and the dynamic part, the L and the M. So this over here, this L and M is basically the two masses which must be included on the shaft. Over here, I could say here, in this case here, there's 1, 2, 3 masses. We have to include a mass there and a mass here at this particular angle to make sure the shaft isn't balanced. So obviously, it was not able to balance. It was not balanced at all. We have a vibratory motion. So that's the idea here. So instead of us having the same plane, it's going to be in a different plane. What it looks like in real life, for instance, is where you have your propeller shaft system, and you have your bearings over there, wherever, well, say it's the journal bearings there and a bearing there, and as it's rotating, you've got the gearbox. Where's the gearbox here? So okay, this is direct drive, but you have, for instance, over here, that rotating, the gearbox rotating on the shaft, and obviously that's not in the same plane, so it has to be now balanced. And another good example is this over here. We have this so-called transmission system of some sort, where you have one gear there, another gear there, another gear there. So this could be a system where you have several masses rotating in different planes. We also have maybe something similar to this. It's 1,002 bearings, and we have one pulley system there and one pulley system there. And we'll be using a similar analysis in the next chapter. And also, if you look at your camshaft, for instance, or even your piston thing, we have masses rotating in different planes. So your cams here on top, your valves are opening and closing. As a cam is rotating up and down, there's one cam there. So this is an example of masses rotating in different planes, just to give you a context of what it actually looks like. It's important for you to note is that there's two types of balances: the static balances, which is the MR, which must equal 0, and the couple, which is the MRL, must equal 0. That's just what it looks like. And how we do it is basically similar to what we did before. I just want to see, yeah, okay. So we do something similar to what we did before, and I'll come back to this. We have to first take the MRL product now, which is now the new thing, and then we have to do the MRL, which is the MRL cos, MRL sine. That's to solve the dynamic part. And then subsequently, we have to do the MR part, which will be the force balance part. And that's the idea of this thing. So there's two different types. Likewise, we have two different graphical polygons rather. One will be the couple polygon, which will be the MRL polygon, which you have to draw based on this. And we have also the force polygon, which is the MR part, which this is essentially demonstrating here, which you're obviously familiar with. This is the static balance part. This is the dynamic balance part, and this is the static balance part over here. What's important to note now, just referring back to this particular thing, when we're doing balancing of masses, we typically choose one mass as a reference. So in this case here, they're saying they've taken the one of the balancing masses L as a reference, and then we basically refer each mass to that. We typically take one of the balancing masses, particularly the one on the left, as a reference. Yeah, so I hope you guys get the gist of this. But now we're looking at a system which essentially looks like, where's that picture now? It looks like this. So one mass, another mass, another mass, and they'll all be rotating at different angles, and we need to find what that mass is there and what that mass is there. And obviously, I'll take you through the problem for the day. So we're going to be doing the analytical method and the graphical, right? This is the book. They don't actually do the analytical yet, so I'll show you how to do it. So it's in a note, not this example. This one, yeah, this one. So it's one of those notes there which I showed you. You can just open it up and see. Okay, just open this up first. Yeah. Okay. Is there any questions so far? Do you guys get what dynamic balancing is about? What do you guys think of this chapter so far? By the way, any takes on it? Nothing. Okay. So what we're typically going to do is now draw a table. Right, so this is the first approach you actually want to do for this type of problems. Let me just make sure it's the right example. Okay, cool. Right, so it's just going to take us a while to finish up this problem, but yeah. So the shaft carries 4 masses A, B, C, and D, different magnitudes, 200, 300, and 400, and revolving at different radii. And okay, so what I want to do now is sketch it like this. I'll sketch it how they typically sketch it. So we have one mass rotating, how do I say, like this? That's A, mass A. And then mass B is rotating 45 degrees relative to that. Mass C is 70 degrees relative to B, so that's like 45 plus 70, 115, something like that. And then we have mass D, which is rotating at 115 from C to D. Can you see, Ms. Mambisa? So at 235, so something like so something like that. Yeah, I'll just have it in mass D. I'm not cheating. That's what I thought. Yeah. Okay, cool. I realized it afterwards writing. Okay, cool. Yeah, so that's the example. Yeah, so can you guys see that? So what I just basically did was sketch. That's that mass. That's mass A. That's 45 degrees. Obviously not to scale. That's C, 110 degrees, and that's mass D. Okay, just to give you an illustration of what's happening. So we can say that's a bearing there. That's fixed there. So this is obviously rotating. And we want to know where do we place what do you call it, these masses. So what they do say here, they give us the radiuses as well. So I'll write that again. They do say that let me just quickly see, blah, blah, blah. They say that from mass, let me just get this right, and planes 300 measured from A, so 400 and 700. Okay, so how far is, I'm trying to just get this right here, the distance between planes A and X and Y is 400 and Y and D is 200. Yeah, that's the radiuses measured from A at 300. Okay, cool. Yeah, so from A to B, this is what I was trying to get. So measured from A to B. So obviously the radiuses are given there. I just want to get my yellow pen. So they're saying from A to B, the distances there is going to be 300 from B to C. They give us B to C. They give us 300, and then what is 400? Measured at A, 300, 400, and 700. And they're saying mass, from A. So mass C would be 400 millimeters. Obviously, you have to bear with me. This is not to scale. So from A, it's 400 millimeters. And then to D, it's I'm just drawing a horrible front view, whatever. That's 700. So this is the distance from here to here, 300, 400, and 700. Okay, that's just the general idea of what it look like. So what the two things you typically want to sketch here is, I'll do it properly now. You first want to have your actual sketch, your space diagram, so to say. That's just that top view kind of thing. So let me just do a space diagram first. So mass A is here, 200 kilograms at the right. This is mass, sorry about this, 300 kilograms at an angle of 45 degrees. That's A, B. And then we have, what's it again? What's B to C? 70, right? So 70 plus 45, I think, will give us 115. So I think that's 115 here. That's C. It's 115. And that's 400. And then we have 120 degrees from C. So that's plus 120. That's 235. Okay. And that's 200 and then 235 over here. Okay. Do we all get that? Do we all understand what's going on here? Can we all see the space diagram? That's looking at it from this view. It'll look like that. This will look like that. This is the center here. You guys all get that? Can you guys see that? Cool. James can see it. Yes, PJ can see it. Okay, cool. And then what we have to do is look. Now we have to look like this. Your next sketch. Balancing is easy, but it can also be hard, right? So this is coming from the side now. And this is what I was essentially doing. So mass A was here. And then mass B. I'm just writing all the masses on the shaft. And then mass D. And then they stated that if you're reading the question here, not like this funny sketch I did, it says in planes measured from A at 300. So that's from A. This is 300 from here to here. From B to C. Obviously, B should be a bit closer. There should have been 400. And then from A to, that must be, say, around 700. Okay. You guys get that? So that's looking at from the side now. That's what it looks like. Obviously at the respective angles. Okay. So now the next thing they said there are two, let me go look at big. The balancing masses are to be placed in planes X and Y. We can call it anything really, M and M, P and Q. The distance between the two planes of A and X is 100. So they're saying that our one balancing mass, which I'll put over here, is somewhere over here. I'll call it X. And it's 100 millimeters away from A. And then they're saying the distance between X and Y is 400. So I'll use another color for that. So X and Y. So somewhere there. in fact, somewhere there rather. Obviously, this is not to scale. It's 400. And let's say it's 400 and between Y and D, so that's the other balancing mass, which I'll make blue color. Blue mass here, Y. So from here to here is 200, and between the two masses is, so yeah, okay, 200 millimeters. Just, yeah. Well, the question states is if the balancing masses revolve in 100 millimeters, so again giving the radius, right? Find the magnitudes and the angular position. So they want to know what's the theta of X and Y, and they want to know the masses of X and the masses of Y, and which positions and what is the mass. Is that clear to everyone? Do you all understand the question? Can we see what's going on? Can we all see what's going on? Any questions so far? Before I move on. Any questions? No questions, guys. PJ, James, Mr. Sima. Okay, cool. Thank you. So what's typically next after you've sketched that? If they didn't give you the sketch, you're going to have to create a table. And that's, so you call it plane, mass, radius, the MR, L, and MRL. So that's what you're going to be looking at. You can obviously include the angle if you want. That's if you really want to do, you can put in the angle if you want. So we're going to have a table. So we start with mass A, right? For plane A for mass A is 200. The radius is given as 80, right? So you put 80 here. And the MR product would be, or rather, 0.08. The MR product is simply 200 times 0.08, and you get 16, right? Kilogram meter. This is what you know already, the MR. X, like I said, X, what we're going to use X as is our reference plane. So it's typically we will refer everything to this plane. It'll make sense why. And we do the same. So we don't know this. We know the radius is 0.1. So our MR will be 0.1 times mx. We do B. B is, what do you call it? 300. And our radius for B is 70. Okay, I'm letting you guys fill in the MRs there for me. For C, we start C, and this Y. So this over here, that there is our balancing mass. We need two. We need one for static and one for dynamic balancing. For C, we have a mass of 400. Y, we obviously don't know the mass. We're still trying to figure that out. And then we have for D for 200. The distance for C is 0.06. This was 0.1. Therefore, this can also be 0.1 my. And then for D, the mass was 0.08. So it's also 16. So can someone give me the what is this? The MR product for B and C, please. So 2.1, the 2.1, 300 times 0.07. should be 21. Not 2.1. 21 and 24. There we go. Cool. Right. So once you have that, that's, by the way, you get a mark for this table. You want to see a mark allocation check test 1, which I posted on Blackboard of last year. Give me like 6 marks. Okay. So now on the dynamic part, we have to look at our lengths now, right? So with the reference planes comes in now is that we have to make this 0. We're assuming that that is, so when I say this is 0, I'm referring to the sketch over here, right? So I'm saying that that's at 0. So that length over there will be 0. So now, if you look where x is, x would be, x is 0, sorry. So therefore, a will be minus 0.1. So sorry, not there. My mistake. So 0 is over here. So this is 0.1 and that is 0. You guys agree with me? Do you understand why this is negative 0.1? That's behind x. This is our new 0. You guys got that? That is for your length part. Does everyone follow with that? Cool. Let's see. Cool. And by the way, this is equally as, you know, it's a very good problem. It's like at seconds level. You can get a problem like this easy for a test or an exam. Obviously, mass B now, mass B will be 300 minus 100, so that will be 0.2. If you agree with me, if you look at the sketch over here, 300 minus 100. Mass C will be 400 minus 100, which will be 0.3. Mass Y, they said they said they 400 millimeters in between, so that's 400. Then mass D will obviously be 0.6. We all happy with these dimensions? Please tell me if you don't understand. It's super important. You get like half a mark for the MRs and half a mark for each, for the MRLs in particular. All right, you'll see where I'm going to with this. It all makes sense soon. Okay. Okay, so if you agree with my dimensions, Mr. Sima and Muda, all you have to do now is find the MRL now. So all you have to do is times MR times L. Give me this value, that value, that value. So obviously this will be 0. So you're just timesing MR times L. This is what MRL means, MR times L. So you can just have all those values there. And you're basically done with the table. Can I get my M or L values? That's the dynamic component of the balancing. So 4.2. What about the first one, Ms. Duba? The 1.61. Yeah, negative 1.6. That's correct. This, yeah. And you said 4.2, 9.6 for D. Yeah, okay, that's fine. Y will be, obviously this is 0.1 times 0.4, which will be 0.04 my. And yep, thank you. What about C? C 7.2. Yep, fantastic. Okay. Right. So, guys, just looking at this table, right? I want you to hone in on something. So when we're doing the analysis, I want you to understand, and even when you do your graphical method for this, is that, can you see that in this MRL column, that the only unknown is this? So even when we start with the analytical, we start with our MRL or couple analysis or polygon. That's where we first start. Once we have this value, we can put it in here. So we first dynamic balance, and then we head off into static balance. So I'm just showing you how to work. So we go on the dynamic side, you solve for this, then you can go on the static side. Once you have that match there, you can actually then just input that, and the only unknown will be then. So I'm just showing you, like, if you're just looking from the table, where you're kind of working towards here. Right. So now we follow a similar procedure. Now, I didn't articulate that, I guess, correctly in terms of the analytical approach, but what it essentially is, we're taking the sum of the MRL now instead of the, you know, I did mention obviously the sum of the MRLs instead of the sum of the MRs now. First, what we do, we actually include the angles if you want, but I'm not gonna do that. No man, why are you not listening? Clicking the wrong thing. So we just say sum of MRL cos theta, and then we populate that, and we say MRL sine theta. So we do exactly the same as what we did before, right? So I'll start with the first one. I think our angles are important. We don't know this angle, so that's angle X, and that's angle Y. This is at 0 degrees, that's at 45. What's from B to C? B to C was 150. No, it's referenced obviously towards 115, or reference from A. And then angle D was 235. I think that's correct. So we're gonna just, for analytical method, we're just gonna obviously just do that now. So MRLs. Okay, so first things first, our first MRL is minus 1.6 cos at 0 degrees. That's our first one. Then I want us to do our second one. I'll explain to you now how it works. Is going to be for B now. B is going to be 4.2 cos 45 plus 7.2 cos 115, and this is also plus 9.6 cos 235. Okay, so obviously I've obviously neglected the X and the Y part deliberately here. We could have included them here and solved them simultaneously, but there is obviously a more better approach in order to solve this, which I will show you. So this is just to solve for your MRL. Okay, so let's just get the total of this, and then can you also get me the sine part of it as well? You'll see how to all work out basically. But what we could have done was just find that first, and I'll show it to you afterwards. Otherwise, it's going to confuse people. Just find the total thing. I will get into that now. MRL for the cos part, right? So yeah, okay, it's 0. Oh yeah, so let me just include this here. I guess plus 0.04 my. I'll just include it here for now. Theta y, cos theta. This is what I was referring to. You guys all agree with this? The 1.6, that's 0. There's nothing there. 4.5, that. that, and that. Are you guys happy with the MRL cos? Hey guys, are you there? Are you lost? What's the final answer here? So can I get a total answer of all of that stuff summed up? 21.58. Is that correct? Are you sure it's 21.58? It shouldn't be 21.58. It's definitely not 21.58. So minus 1.6 cos 0 plus 4.2. Yeah, there we go. It's minus 7.179. So minus 7.179 plus 0.04 my cos that, or that angle. Okay. So do exactly the same for the sine. So that's my first equation. Do the second one. Do it for the second equation. So the second equation you'll get basically something plus 0.04 my sine y. I guess we're going to have to finish this one and do graphical method next week. Okay. Let me get my next one. Let's see. 1.631 is right. Yep, 1.631, definitely positive. That's correct. 1.631. Okay. So that's our. So that is our second equation. Obviously, this is equal to 0. And what you can basically do is just make them equal to each other. 0.7 my equal to each other, or how do I actually or substitute the one terms of the other one? Sorry, not make it equal to one. So you can say, yeah, the smart approach essentially is this, we just divide, instead of me doing the long math, divide 2 by 1. Yeah, you have my sine theta y, right? Divided by, and that's 0.04. So it's like normal sometimes, there is a different way to do it in the typical mathematical way. Cos y, divide that out, and I'm supposed to divide this over here, right? And carry over these ones here. So this will become minus 1.631 divided by minus 7.179. So that's plus, that's plus, that's plus. So dividing like that, I just carried over these values here. That will cancel tan theta y, and you have minus 631 over 7.019. I think it should be correct. And you should get a negative answer, 1.63. Yeah, so what angle do you get there? You guys follow what I did there? I'm just using that basic math in order to. What answer do you guys get? It's a 7. What's a 7.7? Oh, yeah, I see my mistake. Okay. 179. Sorry. So you should get negative 12.79978 degrees. All right. can't see your screen, so I'm sharing. Can't you guys see it? So just refresh on this toolbar. You guys get that angle? Cool. Yep, and that's not the full angle yet. We must still, you know, put it in the right quadrant. And then for us to get, you know, our mass at y, we can just say my sine either one of these equations, sub into 2 or 1. I'm just choosing that one. So sine minus 12,79978 times 0.04, sorry. Obviously, this must be equal to minus 6.31. That equation over there. So let me just get my my. What does my my come out to? Let's just get an my. 631 sine minus 12.79998 times 0.04. Should get 184.05 kilograms. You guys get that? Is there any questions with finding that's still first mass and at that particular angle? I'm going to sort this out now for you. Any questions? You guys get that mass? Just do what? Can you see my screen? And then PJ to find this answer. So we know that this is 12, what? 7,998, right? That's that force there. Sorry, yeah, that angle over there. So this needs to be in that quadrant there. What quadrant did they put there? This mass must it be there? Something feels suspicious with that angle. Okay, I'm happy with it now. Minus 12, it's there. Okay. No, it's fine. That's that angle there. I'll come back to this again. Guys, you get the mass? Did I lose you guys? My silence means that I lost you. Any questions? Woo. Students, can you guys still hear me? I'm not sure you guys went completely silent. PJ's got it. Any questions, guys? Please stop me now. We have this week and next week. And this is fairly tricky, you know what I mean? It's fairly hard. So it's detailed, I think I should say. Okay. Sipo, Johan, Mr. Breert. No questions. Okay, thank you guys. I appreciate that. So now the next part basically is we need to I'm just thinking about something. Okay, I see. Okay, no, it's fine. That's where that thing is. That's where that mess lies. Okay, it's fine. Let's see where that mesh lies. I'll sort it out now. So the next part is to do your MR part. So it's the same thing again. Like I said, reverting back to this over here. Now, balancing is always a heavy thing to do. Like I said, now we found this. We've got MY, and now we have to do our MR. What do you call this? MR. Your force part. Your force. Your static part now. For static balance. So we know where to place that for dynamic balance. For static balance. So now we got to do exactly the same again. Not the same, but MR cos. Sum of MR cos, we make it 0. And the sum of MR sine theta, we make it 0. Okay, so I'll just do, okay, let me just go back here. So it's 16 cos 0 plus 0.1 mx, we don't know where that is, plus, sorry, does it have an angle? So cos, we don't know, cos x, then we have plus 21 cos, was it not, what was it again, 45 I think, then it's going to be 24 cos 115, was it 115, yeah, plus mass, where am I now, 24, oh, then we have the 0.1 times mass y, obviously mass y as a number now, as a value, sorry, cos, what's it, minus 12.7798. Obviously this is the number we have, this is 184.05, and then we have mass d, and mass d was 16 cos 235 degrees. So all we have again one equation again, and then another equation again. But it's obviously there is a more convenient way to sort this out. I'm just letting you know. Instead of doing the math, you can just find the squares and stuff. But anyway, let me get this value. That's all equal to 0. So in the end, we're going to end up with 0.1 mx cos x equals something, yeah, or something plus or minus, let's say plus equals 0, and so that's equation 1. Okay, so let's just get the total of that. What do you guys get? So 16 cos 0, the 21 cos 40, the 24 cos 115, and yeah, there's one thing I'm a bit suspicious about, but I'll just confirm now. Cos stop. Okay. So the one thing I'm just concerned about, okay, that's fine. Okay, so can I get a total of that? We're nearly there, guys. Hope you guys on campus already. Yeah. 200.183. No, it shouldn't be 200. It should be 29.47. That's the cos. Oh, is my mass not? What's my mass? I'm gonna just check. My mass, yeah, at 0.1 times. Remember, yeah, 29.477. Yeah, there we go, 477. That's correct. Yeah, 29.477. That's correct. And then you do the same with the MR cos, so the MR sine. Quickly, obviously this will be 0.1 mx sine of x. It's actually crazy stuff here when I'm looking at it. It'll be plus something and be equal to something, and then equation 2. Okay. That's plus 29.477. That's correct. Just do the sine now. Now the next lesson I have to show you some tricks around. So it's still graphical and then tricks. Ooh. Yeah, it's going to take some time. Okay. Let's just get the sine one now as well. Just make sure you get it. Yeah, is it correct? I think we just got it. Yeah, it's 19.417. Definitely right. 19 plus 19.417. And then again, we do exactly, we divide 2 into 1, obviously, so we can get tan, that's right here. And you're left with sine, tan theta x is basically equal to negative 19.417, which is that there coming over, minus 29.477. And we can just simplify theta x. And what's your theta x? Can I quickly get that? Quickly, let's get the theta x, then 33.37. 33.37, yep, that's perfectly fine. Cool. And then to find your mass, simple, mx, or just equal to 19.417. That's divided by 0.1 times sine of the 33.37. I wonder if this is correct. It's not actually. Let me just confirm something. Cool. Sine 33.37. Just want to see something. Okay. Yeah, okay. Then you should get 353 kilograms. But something else. You guys get this? Let me just conclude now. We basically found both angles, but we need to add 180 to m. What is this? We need to add 180 to the other angle there. Yeah, it's time now already. Okay. So, in summary, that's what we have here. For our dynamic balance, my must be at that angle. And then to find out our angle x, we have to add 180 to that 33.37. And we get 213.37 degrees. So what it means to balance this system of rotating masses, this must be 353 kilograms at 213.37. I recommend going any problem similar to this. Like I said, this is around 20 to 25 marks. The question off the bat, my was 184 point whatever kilograms, and its angle in this case was at minus 12.3 something degrees. I have a question, but I'll leave it for next week. How many marks? That 20 to 25. It's big. I always recommend starting with balancing. Yeah. Okay, guys. It's 22. I don't want to take more time. I hope you enjoyed today's lecture. We'll do the graphical version next, and I'll probably do another problem in balancing. Might start shafts. It just depends on how we're gonna. We might do 2 problems in balancing or something. I don't know. I might start shafts only the other week, the 6th, before you guys close. Okay, guys. Is there any questions? I'll just end session 2 here.